In the last video we talked about the 4 different ways in which nuclei can undergo decay. So we had alpha, beta plus, beta minus and gamma. In this video I'm going to talk a little bit about why these decays happen, and then we're going to look at the equations that govern how fast and how long these decays take. Okay, so the first thing is we need to get our head around that radioactive decay is actually all about nuclear stability. And small nuclei are always going to be more stable than larger ones. So if you remember in the video when I talked about alpha decay, I talked about how it normally happens with really big nuclei. And what I want you to do is just have a little think about why it might be that smaller nuclei are going to be more stable than larger ones, because it's a really important concept. Okay, so having a little think, I hope. First thing we need to think about is what is it that holds the nuclei together inside this nucleus? What glues the nucleons together? Hopefully you're all dredging up the piece of information that says, oh, it's the strong force. And what do we know about the strong force? Strong force is really, really short ranged. So it only acts over a very short distance. So what else is going on inside the nucleus? Well, we're putting protons into the nucleus and they're going to repel each other. And they're being repelled by the electrostatic force. So basically, in bigger atoms, I'm putting in more protons, which makes it more destabilized. We also know that the electrostatic force acts over a long range. So if I've got a big nucleus, I might have nucleons at one side that are not applying the strong force to nucleons on the other side because the nucleus is just too big. But they are still repelling each other because of the electrostatic force. So the smaller ones are going to be stronger, are going to be more stable because the strong force is able to act on all the nucleons, whereas it can't on the larger nuclei. Okay? So if we then plot this graph, just have a little look at this. This is a graph of nuclear stability, and pull my face that way. And what we've plotted here is neutron number against atomic number. And the black dots show you where there are stable nuclei. So we've just talked about why smaller nuclei would be more stable than larger ones, and that's in terms of the strong force acting. But if we look at this now, what we can see is that as those nuclei get larger, in order for them to be stable, the number of neutrons massively increases above the number of protons. This blue line on here would be where the number of neutrons is equal to the number of protons. So down at the bottom I've got, if we're below the line it would be a proton-heavy nuclei. If it's above the line it's a neutron-heavy nuclei. And if we see, in order to be stable, we move further away from the line and further into neutron-rich nuclei. Okay, and that's quite important. I'm just going to pull out some little notes about this. So first thing we can pull out is that beyond 83, so a proton number of 83, the nucleus becomes unstable. So that's kind of like the maximum that you can get to with a stable nuclei. Anything above that and it's going to be unstable, so it will undergo radioactive decay. For the relatively small proton numbers, so Z is less than 20, we find that the strong force dominates, so the charge on the nucleons is pretty insignificant. So whilst they're still relatively small, I don't care about having them mostly be protons or an equal balance of protons to neutrons, because the strong force just takes over and is so strong it doesn't matter. Once I get over the proton number of about 20, I find that I put more neutrons in. And the reason we put the extra neutrons in is because they are extra sources of the strong force without adding extra electrostatic repulsion. So it's kind of like they dilute the effect of the protons by just spreading them out. So it decreases the destabilizing effect of those protons in there and just helps glue it all together a bit more. Okay, so that's kind of looking at how we can make nuclei more stable. So if we do get an unstable nuclei, so we have a balance of protons and neutrons that's unsustainable, the nucleus will undergo radioactive decay. Radioactive decay is just the act of the nucleus rearranging itself so that it becomes more stable, so that it can reach an equilibrium between the strong force and the electromagnetic force. That's why decay happens. It's in order to make the nucleus more stable. Okay, so that's why it happens. So the other thing I said that we would look at is some of the equations and the maths behind it. So a couple of terms we're going to need to get our head around. First one is activity. The activity of a radioactive sample is the rate at which the nuclei decay or disintegrate. And the SI unit of activity is becquerels. Note it is the rate at which something happens, so I'm pretty sure you would be able to tell me what the base unit of becquerels must be. Next one we're going to talk about is the decay constant. And the decay constant is the probability that an individual nucleus will decay per second. I always put this in as a little note because someone always quibbles, but yes, the symbol is lambda, which is also used for wavelength, but because of context, you will never be confused whether they're talking about wavelength or decay constant. So those of you out there tempted to quibble, you know who you are, deal with it. It's never going to be an issue. And lambda, of course, I'm sure you already figured out, is measured in per second. Sometimes you might be given it per hour or per year, if that's more reasonable. But it is a per amount of time because it's per second is its official definition. So if we just think about how these things would be related, if you had a sample of n, so some number of undecayed nuclei, what would the activity be? So in other words, how many nuclei would decay in a second? Because that's what the activity is. So if I wanted to calculate the activity, which is the number that do decay per second, I have the decay constant, which tells me what the probability one of those will decay per second. All I need to do is multiply n by lambda, because n is the number of nuclei and lambda is the probability that any one of those will decay, and that will give me the activity. Right then, half-life, topic or a idea we should already be familiar with. It's the time taken for the mass of the isotope to decrease to half the initial mass, or the time taken for the number of undecayed nuclei to decay to half the number of undecayed nuclei. Radioactive nuclei have all got their own half-lives, and the values vary massively. They can go from millions of years to fractions of seconds. So the question becomes, how are the decay constant and half-life related? So if a nuclide has a large decay constant, is it going to have a long or short half-life? And once you've got the answer to that, you can have a little think about what type of proportionality does that suggest. So if we just have a think, if we've got a big decay constant, that means that we've got a large probability that any given nuclei will decay per second. There's a high probability it'll decay in a given second, then it's going to have a short half-life, isn't it? So if it has a short half-life when it has a large decay constant, that means I'm going to have an inverse proportion relationship. And in fact we do, and it leads us to the fact that the decay constant is proportional to 1 over the half-life, and to be more specific, it's log 2, or 0.693 over the decay constant, or over the half-life. Now this formula is really, really useful, because sometimes it is easier to measure the decay constant, and sometimes it is easier to measure the half-life. This allows us to switch between the two depending on which we could actually measure in a sensible time frame. Okay, so half-life equals log 2 by lambda. Okay, so we're just going to have a little look at using half-lives and calculating with it, which should be something you've done at GCSE, but I just want to be sure that you're really happy with it. So just a little note, inside the nuclear industry, something is considered to no longer be radioactively dangerous after it's undergone 20 half-lives. So a common fission product from a nuclear reactor is cesium-137, and its half-life is 30 years. So the question is then, what fraction would still be active after 20 half-lives? If we're saying that 20 half-lives is when it's safe, what's the fraction that's left that we consider to be safe? Well, there's two ways of calculating this fraction. The GCSE way is probably to do it the long way, which is you go a half of a half for 20 steps. So go to a half, a quarter, an eighth, a 16th, 32nd, 64th, 128th. So I'm going to stop there before I run out of breath, until we get all the way down to 1 over 1048,576. So A, first thing to take away, after 20 half-lives, there is a tiny amount left, which is good. But B, my goodness, that's the long way around the houses. There's a much nicer way. That would be to just do half to the power of 20, and that will tell you what fraction will be left over, because if I raise it to the power of 20, that's exactly the same as doing a half times a half times a half times a half 20 times. Okay, so remember the things you've learnt in maths, because you can apply them in physics in a very helpful way. Okay, so let's just think about how we could figure out if I have a specific sample of an isotope that's going to decay. So if I've got 100 grams of my isotope, after one half-life I'm going to have 50 grams. After two half-lives I'm going to have a half squared times 100, so 25 grams. After three half-lives it'd be a half cubed times 100, which gives me 12.5, and you get the picture. So if I want to figure out how much is left, I can use this idea of raising half to a power. So I do a half to the n, which is the number of half-lives, times the original mass, and that will give me the mass that's left over. Okay? Right then, when we are talking about radioactive decay, there's just a couple of things we need to get in our head. First of all, decay is random, and this means that if it is random, it's going to decay in an exponential manner. Remember that exponential means that a quantity is decreasing by a constant factor in equal intervals of time. That's what exponential means. Remember that, it's come up a lot and we need to get it into our heads. Now, because of that, theoretically, the activity will never ever reach zero, because it's a completely random thing, and we know that exponential trends never actually hit zero. Now, with radioactivity, in reality, eventually the radiation will be indistinguishable from background radiation, which means that as far as we know, it will drop to zero, because we won't be able to tell if it's coming from our radioactive source or if it's just from background radiation. Now, so I've said that radioactive decay is random, and I hope we all know that random means that we can't predict when it's going to happen. The other term that we use to describe radioactivity is spontaneous, and spontaneous just means that it happens without outside influence. So I can't make something decay radioactively. It's going to happen when it wants to happen, in essence. So those are the two terms that we would use to describe radioactive decay. So I've used the big word exponential, which means we have to have an exponential equation. So this is the exponential equation. Daisy, just got to face that way again. So n equals n naught e to the minus lambda t. And in this equation, n is the number of undecayed nuclei, n naught is the original number of undecayed nuclei, then we've just got lambda, which is our decay constant, and t is the amount of time that has passed. Now, I can use this equation in the same form with both activity and count rate. So activity we already talked about. Count rate would just be the number of decays that you are detecting in a given time period, so the number per second. So we have this exponential relationship, and it's quite easy to apply. Now, as we have often done with exponential equations, we can find that it might actually be better to turn it into a straight line. So straight line graphs are more useful. So if I've got n equals n naught e to the minus lambda t, I can take logs of both sides of that equation. So log n equals log of n naught minus lambda t. And that gives me a straight line. So that's in the form of y equals mx plus c. Okay, so our intercept becomes log of n naught. My gradient is minus the decay constant, and I've plotted a graph of log of n against time. And that's going to give me a straight line, and that's how we've reduced it to linear form. That's one you're just going to need to know. Okay, so the next thing we're just going to talk about very quickly is some uses of radioactivity. Now, radioactivity is random, which means that for a given thing I can't predict when it's, for a given nuclei, I can't predict when it will decay. But for large numbers, it becomes extremely predictable, which means that in essence we can use it like a clock. There are two main types of radioactive dating. There's carbon dating and there's argon dating. I'm just going to give you a quick run through of them because there's a chance that they will come up on the exam. So carbon dating uses carbon-14, which is naturally occurring, and carbon-14 gets taken up by all living organisms, and the ratio of carbon-14 to carbon-12 will stay constant for the entire time that that organism is alive, because it's constantly taking in carbon, and that ratio of carbon-14 to carbon-12 is the same as is in the atmosphere. Now, once the organism dies, the ratio of carbon-14 to carbon-12 will decrease, because it's no longer taking in carbon, and the carbon-14 decays. So what we can do is look at how much carbon-14 to carbon-12 is left in a sample, and that will give us an idea of when it died. Now, the half-life of carbon-14 is 5,700 years. Now, because we know its half-life, it's going to decrease in a very predictable manner, and we can calculate the age. Now, things that it's good to do this with are wood, charcoal, bone, and shells of land and sea animals. We can't use it on everything. It had to be organic at some point in order for us to use it. Now, unfortunately, carbon dating is not particularly precise. We know the half-life of carbon-14 to within about 40 years, but therefore, once I get to quite old samples, my uncertainty gets quite big. So for a 50,000-year-old sample, that would give me an uncertainty range of plus or minus 2,000 years, which is not great. Generally, we wouldn't go beyond 100,000 years, but as you can tell, that's still going to give you a pretty broad range for when this thing was dated. This method also makes some big assumptions. It assumes that there was no way that any carbon-14 could be introduced to the sample after it died, and it also assumes that the ratio of carbon-14 to carbon-12 has been constant. So carbon dating is never the only method that you would use to date something. It's useful if you want to corroborate a date, but you wouldn't just use it in isolation. So the other thing I mentioned was argon dating. So very similar thing, only this is looking at rocks, so you can look at inorganic things with this. Ancient rocks trap argon gas. The gas is formed by the decay of K40, so potassium-14 to argon-14. And the half-life of the potassium is 1,250 million years. So again, using the same principle, we can calculate the age of the rock by looking at how much argon is present, because that will tell us how much potassium has decayed, and therefore we can figure out how long it's been there. Okay, that is it on radioactivity. So remember, if you have any questions, just ask when you see me.